Imagine standing on a planet orbiting a star so colossal that it makes our sun look like a mere speck of dust. A star so massive that its gravity bends light, its surface burns at temperatures we can barely comprehend, and its life ends in an explosion so powerful it outshines entire galaxies. These are the universe's most massive stars, celestial giants that defy imagination and shape the very fabric of the cosmos. Today, we're diving into the awe-inspiring world of these stellar behemoths, uncovering 30 mind-blowing facts that will leave you marveling at the sheer scale and power of the universe. From stars that could swallow our solar system whole to the explosive deaths that forge the building blocks of life, this journey will take you to the very edge of what we know about the cosmos. So buckle up and get ready to explore the universe's most massive stars, where every fact is a step deeper into the mysteries of space. Let's begin. Now that we've set the stage for the incredible scale of these cosmic giants, let's dive into what actually makes a star massive. When astronomers talk about massive stars, they're referring to stars that are significantly larger and heavier than our Sun. Specifically, a star is considered massive if it weighs in at more than 8 times the mass of the Sun. To put that into perspective, imagine stacking 8 suns together. That's the minimum size we're talking about here. But some of these stars go far beyond that, reaching masses hundreds of times greater than our Sun. What sets these stars apart isn't just their size, though. Massive stars are also incredibly bright, often shining with a luminosity tens of thousands or even millions of times greater than the Sun. This intense brightness comes from the sheer amount of energy they produce through nuclear fusion in their cores. And while their size and brightness make them stand out, there's a trade-off. Massive stars live fast and die young. Unlike the Sun, which has a lifespan of around 10 billion years, these giants burn through their fuel in just a few million years. Their enormous mass means they consume their fuel at an astonishing rate, leading to shorter, more explosive lives. So when we talk about massive stars, we're talking about celestial powerhouses that dominate their surroundings, but only for a cosmic blink of an eye. Now, let's turn our attention to the largest known star in the universe, UY Scuti. This colossal star is a true titan, holding the record for the largest radius of any star ever discovered. To give you a sense of its sheer size, imagine placing UY Scuti at the center of our solar system. Its outer layers would stretch far beyond the orbit of Jupiter, engulfing everything in its path up to that point. That's right, this star is so enormous that it would dwarf even the largest planets in our cosmic neighborhood. UY Scuti was first identified in the constellation Scutum, and its discovery has been a game-changer in our understanding of stellar sizes. While it's not the most massive star in terms of weight, its incredible volume makes it a standout in the cosmos. Astronomers estimate its radius to be around 1,700 times that of our Sun. To put that into perspective, if the Sun were the size of a golf ball, UY Scuti would be as large as a skyscraper. What makes UY Scuti even more fascinating is its role in helping us understand the limits of stellar size. Stars like this push the boundaries of what we thought was possible, challenging our theories about how stars form and evolve. Its discovery has opened up new questions about the life cycles of hypergiant stars and how they influence their surroundings. So, while UY Scuti may not be the heaviest star out there, its sheer size makes it a true marvel of the universe, a reminder of just how vast and varied the cosmos can be. Now, shifting our gaze to another cosmic giant, let's explore R136A1, the most massive star ever discovered. Nestled within the Tarantula Nebula, this star is a true heavyweight champion of the universe. With a mass over 250 times that of our Sun, R136A1 is a staggering example of how extreme stars can become. To put that into perspective, if our Sun were a feather, R136A1 would be a boulder, its sheer weight is almost unimaginable. But it's not just its mass that makes R136A1 remarkable. This star is a powerhouse of energy, radiating light and heat at an intensity that dwarfs most other stars. Its surface temperature is scorching, reaching tens of thousands of degrees, and its luminosity is millions of times greater than that of the Sun. This incredible energy output creates intense stellar winds, which blast outwards at speeds of several million miles per hour. These winds carve out vast regions of space, shaping the surrounding nebula and influencing the birth of new stars. R136A1's impact on its environment is profound. Its radiation is so powerful that it ionizes the gas around it, creating glowing clouds of plasma that light up the Tarantula Nebula. This star is also a key player in the life cycle of its galaxy, as its winds and eventual supernova will seed the cosmos with heavy elements essential for future star and planet formation. However, such extreme mass comes at a cost. R136A1 burns through its fuel at an astonishing rate, meaning its lifespan is incredibly short, just a few million years compared to the billions of years smaller stars like our Sun enjoy. This fleeting existence makes R136A1 a rare and fascinating object, offering astronomers a glimpse into the lives of the universe's most extreme stars. As we continue our journey through the cosmos, R136A1 stands as a testament to the incredible diversity and power of massive stars, reminding us just how dynamic and awe-inspiring the universe truly is. Now, let's turn our attention to the very beginning of a massive star's life, how these colossal giants come into existence. Unlike smaller stars, massive stars are born in some of the most extreme environments in the universe, dense molecular clouds. These clouds, often referred to as stellar nurseries, are vast regions filled with gas and dust where the seeds of stars are sown. The formation of a massive star begins with gravity pulling together clumps of gas and dust within these clouds. As these clumps grow denser, they start to collapse under their own weight, heating up in the process. This is where the magic happens. Gravity continues to compress the material, and the temperature at the core rises until nuclear fusion ignites, marking the birth of a star. But for massive stars, the process is far more intense. They require an enormous amount of material to form, often gathering hundreds of times the mass of our Sun. This rapid accumulation of gas and dust is known as accretion, and it's a delicate balancing act. If too much material falls in too quickly, the star can become unstable. On the other hand, if the process is too slow, the star might not grow massive enough to shine as brightly as it does. One of the biggest challenges in studying massive star formation is their rarity. These stars are much less common than their smaller counterparts, making them harder to observe. Additionally, their formation happens quickly on a cosmic timescale and often in regions obscured by thick clouds of dust. This means astronomers have to rely on advanced tools like infrared telescopes to peer through the veil and catch a glimpse of these stellar behemoths in their infancy. Despite these challenges, scientists have made remarkable progress in understanding how massive stars form. They've discovered that these stars often form in clusters, surrounded by smaller stars, and that their intense radiation and stellar winds can influence the formation of neighboring stars. This interplay of forces highlights just how interconnected the processes of star formation are, shaping the galaxies we see today. As we move forward, the story of massive stars continues to unfold, revealing not just how they form, but also how they shape the universe around them. Their birth is a testament to the power of gravity and the intricate dance of matter in the cosmos. Now, let's shift our focus to a fascinating aspect of massive stars: their surprisingly short lives. While stars like our Sun can shine steadily for billions of years, massive stars live fast and die young. Their immense size and mass come with a price, they burn through their fuel at an astonishing rate, leading to lifespans that are mere cosmic blinks compared to smaller stars. The key to understanding this lies in the process of nuclear fusion. In the core of a star, hydrogen atoms fuse together to form helium, releasing energy in the process. For smaller stars, this happens at a relatively slow and steady pace, allowing them to sustain their energy output for billions of years. But for massive stars, the story is very different. Their enormous mass creates immense pressure and heat at their cores, accelerating the rate of fusion to extreme levels. Imagine a car engine running at full throttle. It burns through fuel much faster than one idling at a steady pace. That's exactly what happens in massive stars. Their cores are like cosmic engines operating at maximum capacity, consuming their hydrogen fuel at a staggering rate. As a result, these stars can exhaust their fuel in just a few million years, a tiny fraction of the Sun's lifespan. This rapid consumption of fuel doesn't just shorten their lives, it also makes them incredibly luminous. Massive stars shine with a brilliance that can outshine entire galaxies, but this comes at the cost of their longevity. The more massive the star, the faster it burns through its fuel and the shorter its life becomes. But the story doesn't end there. As these stars exhaust their hydrogen, they begin fusing heavier elements like helium, carbon, and oxygen. Each new stage of fusion happens faster than the last, further shortening their lifespans. This relentless cycle of fusion and fuel consumption is what ultimately leads to their dramatic and explosive deaths, which we'll explore in more detail later. The short lives of massive stars are a reminder of the delicate balance that governs the universe. Their brilliance and power come at the cost of fleeting existence, yet their impact on the cosmos is profound. As we continue, we'll see how these brief but intense lives shape the universe in ways that last far longer than the stars themselves. Now, let's dive into one of the most awe-inspiring events in the universe, the supernova explosion. When a massive star reaches the end of its life, it doesn't fade away quietly. Instead, it goes out in a blaze of glory, unleashing an explosion so powerful that it can outshine entire galaxies for a brief moment. This is the dramatic finale of a massive star's existence, and it's a process that shapes the cosmos in profound ways. The journey to a supernova begins deep within the star's core. As we've discussed, massive stars burn through their fuel at an incredible rate, fusing heavier and heavier elements as they go. But this process can't continue forever. Eventually, the star's core becomes so dense that it's primarily made of iron. Unlike lighter elements, iron doesn't release energy when fused, it actually absorbs it. This marks the beginning of the end. With no energy being produced to counteract the crushing force of gravity, the core collapses in on itself in a matter of seconds. This collapse triggers a shock wave that ripples outward through the star, tearing it apart in a cataclysmic explosion. The energy released in this moment is staggering, equivalent to the brightness of billions of stars combined. For a brief time, the supernova can outshine its entire host galaxy, making it one of the most luminous events in the universe. But the impact of a supernova goes far beyond its incredible brightness. These explosions scatter the elements forged in the star's core like carbon, oxygen, and even gold across space. These elements become the building blocks for new stars, planets, and even life itself. In a very real sense, we owe our existence to the supernova of ancient massive stars. Supernova also leave behind remarkable remnants. Depending on the size of the original star, the explosion can create a neutron star, an incredibly dense object where a teaspoon of material would weigh billions of tons, or, in the case of the most massive stars, a black hole. These remnants continue to influence their surroundings, shaping the fabric of the universe long after the star itself has vanished. The supernova explosion is a testament to the incredible power and beauty of massive stars. Though their lives are short, their deaths are transformative, leaving a lasting legacy that echoes across the cosmos. As we move forward, we'll explore how these explosive events contribute to the evolution of galaxies and the creation of the heaviest elements in the universe. Now, let's turn our attention to what remains after the spectacular fireworks of a supernova. When a massive star explodes, it doesn't just vanish into nothingness. It leaves behind some of the most fascinating and mysterious objects in the universe: neutron stars and black holes. These remnants are the final chapters in the life story of a massive star, and they play a crucial role in shaping the cosmos. The fate of a massive star's core depends on its mass. If the core left behind after the supernova is between about 1.4 and 3 times the mass of our Sun, it collapses into a neutron star. Imagine squeezing the entire mass of a star into a sphere no larger than a city. The result is an object so dense that a single teaspoon of its material would weigh billions of tons. Neutron stars are incredibly hot, spin rapidly, and often have powerful magnetic fields. Some of them, known as pulsars, emit beams of radiation that sweep across space like cosmic lighthouses, making them some of the most precise clocks in the universe. But if the core is more than about 3 times the mass of the Sun, the collapse doesn't stop at a neutron star. Instead, the core continues to compress until it forms a black hole, a region of space where gravity is so intense that not even light can escape. Black holes are the ultimate cosmic enigmas, bending the fabric of space and time around them. They can grow by consuming nearby matter, and their presence can influence entire galaxies. Supermassive black holes, for example, are thought to lie at the heart of most galaxies, including our own Milky Way. Both neutron stars and black holes are more than just remnants, they're active players in the universe. Neutron stars can collide, creating ripples in space-time known as gravitational waves and producing heavy elements like gold and platinum. Black holes, on the other hand, can power some of the brightest objects in the universe, such as quasars, by heating the material that spirals into them. These remnants remind us that even in death, massive stars continue to shape the cosmos. Their influence extends far beyond their explosive ends, leaving behind objects that challenge our understanding of physics and inspire awe in anyone who studies them. As we move forward, we'll explore how these remnants contribute to the evolution of galaxies and the creation of the heaviest elements in the universe. Now, let's shift our focus to the broader impact of massive stars on the galaxies they call home. These colossal stars are not just isolated wonders, they are cosmic architects, shaping the very structure and evolution of galaxies. Through their explosive deaths as supernova, their powerful stellar winds, and their role in creating heavy elements, massive stars leave an indelible mark on the universe. When a massive star explodes as a supernova, it releases an enormous amount of energy and matter into its surroundings. This explosion can trigger shock waves that compress nearby gas and dust, sparking the birth of new stars. In this way, the death of one massive star can lead to the creation of many others, creating a cycle of stellar life and death that drives the evolution of galaxies. But the influence of massive stars doesn't end with supernova. Even during their lifetimes, these stars emit intense stellar wind streams of charged particles that blow outward at incredible speeds. These winds can carve out vast cavities in the surrounding gas, shaping the structure of the galaxy and influencing where new stars can form. In some cases, these winds can even push gas out of a galaxy entirely, regulating its growth and star formation rate. Perhaps one of the most profound contributions of massive stars is their role in creating heavy elements. Through nuclear fusion in their cores and the explosive processes of supernova, massive stars produce elements like carbon, oxygen, and iron, elements essential for planets, life, and even the stars themselves. When these stars die, they scatter these elements into space, enriching the galaxy and providing the raw materials for future generations of stars and planets. Massive stars also play a key role in triggering star formation in nearby regions. Their intense radiation and winds can compress surrounding gas clouds, creating dense pockets where gravity takes over and new stars begin to form. This process, known as triggered star formation, ensures that the influence of massive stars extends far beyond their immediate surroundings, shaping entire regions of a galaxy. In essence, massive stars are the engines of galactic evolution. Their lives and deaths drive the cycles of matter and energy that shape galaxies, from the birth of new stars to the creation of the elements that make up our world. As we continue our journey through the universe's most massive stars, we'll see how their legacy extends even further, influencing the cosmos on the grandest scales. Now, let's dive into one of the most fascinating roles massive stars play in the cosmos, creating the heaviest elements in the universe. While stars like our Sun fuse hydrogen into helium and lighter elements, it's the massive stars that take this process to the next level. Through their incredible power, they forge elements heavier than iron, elements that are essential for life as we know it and the very fabric of the universe. The process begins deep within the cores of massive stars, where temperatures and pressures are unimaginably high. Here, nuclear fusion doesn't stop at lighter elements like carbon or oxygen. Instead, it continues step by step, creating heavier elements like silicon, sulfur, and eventually iron. But iron is where things get interesting. Unlike lighter elements, iron doesn't release energy when it fuses, it actually absorbs it. This marks the beginning of the end for a massive star, as its core can no longer support itself against gravity. When the core collapses, the star explodes in a supernova, one of the most energetic events in the universe. It's during this explosion that something extraordinary happens. The intense heat and pressure of the supernova create the perfect conditions for a process called nucleosynthesis. This is where elements heavier than iron, like gold, platinum, and uranium, are formed. These elements are then scattered into space, enriching the surrounding gas and dust with the building blocks of planets, moons, and even life. But why are these heavy elements so important? Without them, the universe as we know it wouldn't exist. Elements like carbon, oxygen, and nitrogen are the foundation of life, but heavier elements play crucial roles too. For example, iron is essential for the formation of planetary cores, while elements like copper and zinc are vital for biological processes. Even the technology we use every day, from smartphones to spacecraft, relies on these heavy elements forged in the hearts of massive stars. In a way, massive stars are the ultimate cosmic alchemists. They take the simplest elements and transform them into the complex materials that make up our world. Every atom of gold in your jewelry, every piece of iron in your car, and every trace of uranium in the Earth's crust owes its existence to these incredible stars. As we continue our exploration of the universe's most massive stars, we'll see how their influence extends even further, shaping not just galaxies but the very elements that define our existence. Next, we'll uncover the mysteries of hypergiant stars, the rarest and most extreme members of the massive star family. Now, let's turn our attention to one of the most extraordinary members of the massive star family, hypergiant stars. These celestial giants are the rarest and most extreme stars in the universe, pushing the boundaries of what we thought possible for stellar size and brightness. Hypergiants are so massive and luminous that they dwarf even the largest stars we've discussed so far, making them a fascinating yet elusive subject for astronomers. Hypergiant stars are defined by their sheer size and incredible energy output. Some of these stars can be hundreds of times more massive than our Sun and millions of times brighter. To put that into perspective, if a hypergiant were placed in the center of our solar system, its outer layers could extend beyond the orbit of Jupiter. Their luminosity is so intense that they outshine entire galaxies for brief moments, making them some of the brightest objects in the cosmos. But with such extreme characteristics come significant challenges. Hypergiant stars have incredibly short lifespans, often lasting only a few million years, a blink of an eye in cosmic terms. This makes them incredibly rare and difficult to study. By the time astronomers detect a hypergiant, it may already be nearing the end of its life, ready to explode in a supernova or collapse into a black hole. Adding to the challenge is the fact that hypergiants are often shrouded in thick clouds of gas and dust, remnants of their own intense stellar winds. These winds, driven by the star's immense radiation, blow away its outer layers at incredible speeds, creating stunning nebulae around the star. While these nebulae are beautiful to observe, they also obscure the hypergiant itself, making it harder for scientists to study its properties in detail. Despite these challenges, hypergiant stars offer invaluable insights into the life cycles of the most massive stars. Their extreme behavior helps us understand how stars evolve, how they influence their surroundings, and how they ultimately meet their dramatic end. Studying hypergiants also gives us clues about the early universe, where such massive stars were more common and played a crucial role in shaping the cosmos. As we continue our journey through the universe's most massive stars, we'll explore another fascinating concept, the Eddington limit. This is the point where a star's radiation pressure becomes so strong that it begins to overcome gravity, and it's a phenomenon that hypergiant stars push to the extreme. Stay tuned as we uncover how these cosmic titans balance on the edge of stability, defying the very forces that hold them together. Now, let's dive into a concept that defines the very limits of a star's existence, the Eddington limit. This is the point where a star's radiation pressure becomes so intense that it begins to counteract the force of gravity, the very force that holds the star together. For massive stars, especially hypergiants, this limit is not just a theoretical boundary, it's a constant battle for survival. The Eddington limit is named after the British astrophysicist Arthur Eddington, who first described this delicate balance between radiation and gravity. Essentially, it's the maximum luminosity a star can achieve before the outward push of its radiation overpowers the inward pull of gravity. When a star reaches this limit, it starts to lose its outer layers at an incredible rate, shedding material into space in the form of intense stellar winds. For massive stars, this limit is a critical factor in their stability. Hypergiants, for example, are so luminous that they often operate right at the edge of the Eddington limit. Their radiation pressure is so strong that it can blow away their outer layers, creating the stunning nebulae we often see around them. This constant loss of material not only shapes their surroundings but also shortens their already brief lifespans. But what happens when a star exceeds the Eddington limit? In extreme cases, the radiation pressure can become so overwhelming that it disrupts the star's structure, leading to instability and even catastrophic events like supernova. For the most massive stars, this limit is a constant reminder of their precarious existence, a balancing act between brilliance and destruction. Understanding the Eddington limit also helps astronomers explain why some stars appear to defy our expectations. For instance, certain hypergiants seem to shine brighter than the limit allows, but this is often due to their complex environments, such as the presence of dense stellar winds or surrounding nebulae, which can scatter and amplify their light. As we continue to explore the universe's most massive stars, the Eddington limit serves as a crucial piece of the puzzle, helping us understand how these cosmic giants live, evolve, and ultimately meet their dramatic end. Next, we'll take a closer look at another fascinating type of massive star, Wolf-Rayet stars, and how their unique characteristics set them apart in the stellar family. Now, let's turn our attention to a truly unique class of stars, Wolf-Rayet stars. These cosmic powerhouses are unlike anything else in the universe, defined by their extreme characteristics and dramatic life cycles. Wolf-Rayet stars are massive stars that have shed their outer hydrogen layers, revealing the hotter, helium-rich core beneath. This process gives them a distinct appearance and sets them apart from other stars in the stellar family. What makes Wolf-Rayet stars so fascinating is their intense stellar winds. These winds are among the strongest in the universe, blowing at speeds of up to several thousand kilometers per second. As a result, these stars are constantly losing mass, ejecting material into space at an astonishing rate. This creates a glowing halo of gas and dust around them, often visible as stunning nebulae. But why do Wolf-Rayet stars lose their outer layers in the first place? It all comes down to their immense size and luminosity. These stars are so massive and bright that their radiation pressure pushes their outer layers away, stripping them of hydrogen and exposing their cores. This process not only shapes their appearance but also influences their surroundings, enriching the interstellar medium with heavy elements like carbon and oxygen. The role of Wolf-Rayet stars in the universe is significant. They act as cosmic forges, producing and dispersing elements that are essential for the formation of planets, stars, and even life itself. Their stellar winds and eventual supernova explosions contribute to the chemical evolution of galaxies, making them key players in the cosmic cycle of matter. However, the life of a Wolf-Rayet star is short and intense. Due to their rapid mass loss and high energy output, these stars have relatively short lifespans, often ending in spectacular supernova explosions. In some cases, they may even collapse directly into black holes, leaving behind a legacy of energy and matter that continues to shape the universe. Wolf-Rayet stars are a reminder of the incredible diversity and dynamism of the cosmos. Their unique characteristics and dramatic fates offer valuable insights into the life cycles of massive stars and their impact on the universe. As we continue our journey through the mysteries of the universe's most massive stars, we'll next explore an even more explosive phenomenon, the mystery of pair instability supernova. Now, let's dive into one of the most explosive and mysterious phenomena in the cosmos, pair instability supernova. These rare cosmic events are unlike any other supernova, and they occur in the most massive stars imaginable, those with masses between 100 and 300 times that of our Sun. But what makes pair instability supernova so unique? It all comes down to a delicate balance, or rather, an imbalance of forces within the star. In a typical massive star, the intense heat and pressure at its core allow nuclear fusion to occur, creating energy that keeps the star stable. However, in extremely massive stars, something extraordinary happens. When the core temperature reaches staggering levels, billions of degrees, the energy becomes so high that it starts producing pairs of electrons and their antimatter counterparts, positrons. This process, known as pair production, reduces the pressure inside the core, causing it to collapse under its own gravity. But here's where things get explosive. As the core collapses, temperatures skyrocket even further, reigniting nuclear fusion in a runaway reaction. This sudden burst of energy doesn't just stabilize the star, it tears it apart in a cataclysmic explosion. Pair instability supernova are so powerful that they can outshine entire galaxies for a brief moment, releasing more energy than a typical supernova by a factor of 10 or more. What makes these events even more fascinating is their rarity. Pair instability supernova require stars of a very specific mass range, too small, and the star won't reach the necessary conditions, too large, and it might collapse directly into a black hole without exploding. This narrow window makes them incredibly rare, with only a handful of candidates observed in the universe so far. The aftermath of a pair instability supernova is equally intriguing. Unlike other supernovae, which leave behind neutron stars or black holes, these explosions can completely obliterate the star, leaving no remnant behind. Instead, they scatter vast amounts of heavy elements like iron and nickel into space, enriching the surrounding interstellar medium and contributing to the formation of new stars and planets. Pair instability supernova are a testament to the extremes of stellar physics. They challenge our understanding of how stars live and die, offering a glimpse into the most violent and energetic processes in the universe. As we continue our exploration of the cosmos, these rare events remind us just how much there is still to discover. Next, we'll turn our attention to the brightest stars in the universe and the incredible impact they have on their galaxies. Now, let's shift our gaze to the stars that light up the cosmos like no others, the brightest stars in the universe. These celestial giants don't just shine, they dominate the brightness of their galaxies, outshining countless other stars combined. Among these luminous titans, one star stands out as a prime example: Eta Carinae. Eta Carinae is a hypergiant star located in the Carina Nebula, and it's one of the most luminous stars ever discovered. At its peak, it can shine with the brightness of 5 million suns. But what makes Eta Carinae truly fascinating is its dramatic and unpredictable behavior. In the mid-19th century, it underwent a massive outburst, becoming the second brightest star in the night sky for a brief period. This event, known as the Great Eruption, ejected an enormous amount of material into space, creating the stunning homunculus nebula that surrounds it today. Even now, Eta Carinae remains a star of extremes. Its brightness fluctuates wildly, and astronomers believe it's on the brink of another colossal explosion, one that could rival the power of a supernova. This instability is a hallmark of massive stars, which burn through their fuel at an astonishing rate, leading to dramatic changes in their luminosity and structure. But Eta Carinae isn't alone in its brilliance. Stars like Rigel in the Orion constellation and Deneb in Cygnus also rank among the brightest in the night sky, each shining with the intensity of tens of thousands of suns. These stars are not just beacons in the darkness, they play a crucial role in shaping their galaxies. Their intense radiation and stellar winds influence the formation of new stars and planets, while their eventual deaths as supernova or hypernova enrich the cosmos with heavy elements essential for life. The brightness of these stars isn't just a spectacle, it's a window into the life cycles of the universe's most massive and energetic objects. By studying stars like Eta Carinae, astronomers gain insights into the processes that drive stellar evolution and the forces that shape galaxies. Next, we'll explore how the intense stellar winds from these massive stars sculpt their surroundings, creating some of the most breathtaking nebulae in the universe. Now, let's turn our attention to the invisible forces that massive stars unleash into the cosmos' stellar winds. These aren't the gentle breezes you might feel on Earth. They're powerful streams of charged particles racing outward from the star's surface at incredible speeds. For massive stars, these winds are so intense that they can reshape entire regions of space, leaving behind some of the most stunning and complex structures in the universe. Take, for example, the Carina Nebula, home to Eta Carinae. The stellar winds from this hypergiant star have carved out vast cavities in the surrounding gas and dust, creating intricate patterns and towering pillars. These winds don't just push material away, they compress it, triggering the collapse of nearby gas clouds and sparking the birth of new stars. In this way, massive stars act as cosmic sculptors, shaping their environments and influencing the next generation of stellar objects. But the impact of stellar winds goes beyond just creating beautiful nebulae. They also play a crucial role in the life cycle of galaxies. As these winds sweep through space, they carry with them heavy elements forged in the hearts of massive stars. When these elements are eventually incorporated into new stars and planets, they become the building blocks for everything from rocky worlds to the molecules of life. One of the most dramatic examples of stellar winds in action can be seen in the Orion Nebula. Here, the winds from massive stars like those in the Trapezium cluster have blown away much of the surrounding gas, revealing a dazzling array of young stars and protoplanetary disks. These winds not only clear the way for new stars to shine, but also help regulate the rate of star formation in the region. The power of stellar winds is a testament to the immense energy of massive stars. Even as they burn through their fuel at a breakneck pace, they continue to shape the universe around them, leaving a lasting legacy long after they've faded from view. Next, we'll dive into one of the most explosive phenomena linked to massive stars: gamma-ray bursts the most energetic events in the cosmos. Now, let's shift our focus to one of the most astonishing and violent events in the universe, gamma-ray bursts. These bursts are the most energetic explosions known to science, and they are directly linked to the deaths of massive stars. When a massive star reaches the end of its life and collapses, it can trigger a cataclysmic event so powerful that it releases more energy in a few seconds than our Sun will emit over its entire lifetime. This energy is concentrated into a narrow beam of gamma rays, the most energetic form of light, which can travel across billions of light years before reaching us. Gamma-ray bursts are so intense that they can outshine entire galaxies for a brief moment. But what makes them even more fascinating is how they form. In many cases, these bursts occur when a massive star collapses into a black hole. As the star's core implodes, it sends out jets of material at nearly the speed of light. These jets pierce through the star's outer layers, creating a gamma-ray burst that can be detected across the universe. Another scenario involves the collision of two neutron stars, which also produces a burst of gamma rays, though these are typically shorter in duration. Detecting gamma-ray bursts is no small feat. They are fleeting, often lasting only a few milliseconds to several minutes. To catch these events, astronomers rely on specialized satellites like NASA's Swift and Fermi missions, which are designed to scan the skies for these sudden flashes of gamma rays. Once detected, telescopes around the world quickly pivot to observe the afterglow, a fading light that lingers after the burst, providing clues about its origin and the environment in which it occurred. The significance of gamma-ray bursts extends far beyond their sheer power. They serve as cosmic beacons, allowing scientists to study the early universe. Because these bursts are so bright, they can be seen from incredible distances, offering a glimpse into the conditions of the universe when it was just a fraction of its current age. They also help astronomers understand the life cycles of massive stars and the processes that lead to the formation of black holes and neutron stars. But gamma-ray bursts aren't just tools for studying the cosmos, they also pose intriguing questions about their potential impact on life. If a gamma-ray burst were to occur too close to Earth, its intense radiation could strip away our planet's ozone layer with devastating consequences for life. Fortunately, such events are extremely rare, and the likelihood of one occurring nearby is incredibly low. As we continue to explore the universe, gamma-ray bursts remind us of the incredible forces at play in the cosmos. They are a testament to the dramatic lives and deaths of massive stars, and they offer a window into some of the most extreme environments in existence. Next, we'll delve into the challenges astronomers face when studying these colossal stars and the mysteries they continue to unravel. Now, let's turn our attention to the challenges astronomers encounter when studying these colossal stars. Observing massive stars is no easy task, and it comes with a unique set of hurdles that make them some of the most elusive objects in the universe. One of the biggest obstacles is their sheer distance. Many of these stars are located in far-off galaxies or dense star-forming regions, making them incredibly difficult to observe in detail. Even with the most advanced telescopes, capturing clear images of these distant giants requires precision and patience. Another challenge lies in their short lifespans. Unlike smaller stars like our Sun, which can burn steadily for billions of years, massive stars live fast and die young. Their intense nuclear reactions cause them to burn through their fuel in just a few million years, leaving astronomers with a narrow window to study them. By the time we detect a massive star, it might already be nearing the end of its life, making it a race against time to gather data before it explodes in a supernova or collapses into a black hole. Adding to the complexity is the interference from dust and gas. Massive stars often form in dense molecular clouds, surrounded by thick layers of cosmic material that can obscure our view. This dust and gas not only block visible light but also absorb other forms of radiation, making it harder to study these stars across different wavelengths. To overcome this, astronomers rely on infrared and radio telescopes, which can peer through the cosmic haze and reveal the hidden details of these stellar giants. Despite these challenges, the study of massive stars continues to push the boundaries of our understanding. Each observation, no matter how difficult, brings us closer to unraveling the mysteries of their formation, evolution, and ultimate fate. As we move forward, we'll explore how these stars have shaped the universe since its earliest days, leaving an indelible mark on the cosmos. Now, let's take a step back in time and explore how massive stars have played a pivotal role in shaping the universe as we know it. From the earliest moments of cosmic history, these stellar giants have been instrumental in transforming the cosmos, leaving a lasting legacy that continues to influence the fabric of space itself. One of their most significant contributions is their role in reionization, a critical phase in the universe's evolution. After the Big Bang, the universe was a dark, dense soup of neutral hydrogen gas. But as the first massive stars ignited, their intense ultraviolet radiation began to ionize this gas, stripping electrons from atoms and lighting up the cosmos. This process, known as reionization, marked the end of the cosmic dark ages and paved the way for the transparent universe we observe today. But the impact of massive stars doesn't stop there. These celestial powerhouses are also the primary factories for creating heavy elements, the building blocks of everything from planets to life itself. Through their nuclear furnaces, massive stars fuse lighter elements like hydrogen and helium into heavier ones, such as carbon, oxygen, and iron. When these stars eventually explode as supernova, they scatter these elements across the cosmos, enriching the interstellar medium and providing the raw materials for future generations of stars, planets, and even living organisms. Without the contributions of massive stars, the universe would lack the diversity of elements necessary for the complexity we see today. Their influence extends even further, shaping the structure of galaxies and triggering new waves of star formation. The shock waves from supernova explosions compress nearby gas clouds, sparking the birth of new stars and perpetuating the cycle of cosmic creation. In this way, massive stars are not just fleeting giants but key players in the ongoing story of the universe. As we look to the stars above, we're witnessing the echoes of their immense power and the indelible mark they've left on the cosmos. Next, we'll delve into how these stars are often found in the largest star clusters, where their collective brilliance illuminates the mysteries of stellar evolution. Now, let's turn our gaze to the bustling neighborhoods of the cosmos' massive star clusters. These dense gatherings of stars are like cosmic cities, teeming with activity and home to some of the most massive stars in the universe. Among the most famous of these clusters are the Tarantula Nebula and the Orion Nebula, both of which serve as stellar nurseries where massive stars are born and thrive. These clusters are not just random collections of stars. They are dynamic environments where gravity, gas, and radiation interact in complex ways to shape the lives of their inhabitants. In these clusters, massive stars often dominate the scene, their intense light and energy influencing everything around them. The Tarantula Nebula, located in the Large Magellanic Cloud, is one of the most active star-forming regions known. It's home to R136A1, the most massive star we've discovered, and countless other stellar giants. Similarly, the Orion Nebula, a familiar sight in our own galaxy, is another hotspot for massive stars. These clusters act as cosmic laboratories, giving astronomers a front-row seat to study the birth and evolution of massive stars in real time. But what makes these clusters so special? It's their ability to foster star formation on a grand scale. The gravitational pull of the cluster compresses gas and dust, creating the perfect conditions for new stars to ignite. Massive stars, with their powerful radiation and stellar winds, further shape these environments. They carve out bubbles in the surrounding gas, triggering shock waves that can compress nearby material and spark the birth of even more stars. This cycle of creation and destruction ensures that star clusters remain vibrant and ever-changing. Interestingly, these clusters also provide clues about the early universe. The conditions within them mimic those of the primordial cosmos, where the first stars and galaxies formed. By studying these clusters, scientists can piece together the story of how the universe evolved from a sea of gas to the structured, star-filled expanse we see today. As we continue to explore these stellar metropolises, we uncover not just the secrets of massive stars, but also the broader narrative of cosmic history. Next, we'll dive into the scorching temperatures of these stellar giants and how they shape their dazzling appearances. Now, let's turn up the heat literally as we explore the scorching temperatures of massive stars. These stellar giants don't just shine brighter than most stars, they burn hotter too. The surface temperatures of massive stars often exceed 30,000 Kelvin, a staggering number when compared to our Sun, which sits at a relatively mild 5,700 Kelvin. To put that into perspective, if the Sun were a warm summer day, a massive star would be like standing in the heart of a blazing furnace. This extreme heat isn't just a random fact, it has profound implications for how these stars look and behave. The higher the temperature, the more energy a star emits, and massive stars are powerhouses of radiation. Their intense heat causes them to glow in the blue or white part of the light spectrum, giving them their characteristic dazzling appearance. In contrast, cooler stars like our Sun emit more red or yellow light. This difference in color isn't just cosmetic, it tells astronomers a lot about a star's age, size, and composition. But the heat of massive stars does more than just determine their color. It also shapes their spectra, the unique fingerprint of light that reveals the elements present in a star. At such high temperatures, atoms in the outer layers of massive stars become highly energized, causing them to emit light at specific wavelengths. This creates distinct spectral lines that scientists use to study the star's chemical makeup and physical properties. For example, the presence of certain elements like helium or carbon can indicate how far along a star is in its life cycle. Interestingly, the extreme temperatures of massive stars also influence their surroundings. Their intense radiation can ionize nearby gas, stripping electrons from atoms and creating glowing nebulae. These nebulae, often seen as colorful clouds in space, are a direct result of the heat and energy pouring out from these stellar giants. It's a reminder that massive stars don't just exist in isolation, they shape the very fabric of their cosmic neighborhoods. As we move forward, we'll explore how these temperatures and colors make massive stars some of the most visually striking objects in the universe, and what that means for our understanding of the cosmos. Now let's paint a picture of the cosmos with the vibrant hues of massive stars. The color of a star is more than just a visual treat, it's a direct reflection of its temperature. Massive stars, with their surface temperatures soaring above 30,000 Kelvin, radiate an intense blue or white light. This is because the hotter a star is, the more it emits light at shorter wavelengths, which our eyes perceive as blue or white. In contrast, cooler stars like our Sun glow with warmer tones of yellow or red as they emit light at longer wavelengths. But why are these dazzling blue and white stars so rare in the night sky? The answer lies in their lifespans. Massive stars burn through their fuel at an astonishing rate, living fast and dying young. While smaller stars like our Sun can shine steadily for billions of years, massive stars exhaust their energy in just a few million years. This means that at any given time, there are far fewer of these luminous giants lighting up the cosmos compared to their smaller, longer-lived counterparts. The rarity of blue and white stars also makes them a treasure for astronomers. Their striking colors and intense brightness provide valuable clues about their composition, age, and the environments they inhabit. For example, a blue star's light can reveal the presence of heavy elements like oxygen or nitrogen in its atmosphere, offering insights into the star's history and the processes shaping its evolution. Interestingly, the color of massive stars also influences how we perceive the night sky. While most stars appear as faint, twinkling points of light, the brightest blue and white stars stand out like cosmic beacons. Stars like Rigel in the constellation Orion or Sirius, the brightest star in our night sky, captivate us with their brilliance and serve as reminders of the incredible diversity of stellar objects in the universe. As we continue our journey, we'll uncover how these colors and temperatures not only define the appearance of massive stars, but also play a crucial role in their interactions with the cosmos around them. Now, let's turn our attention to a force that shapes the very fabric of massive stars' magnetic fields. These invisible yet powerful fields play a crucial role in the lives of these celestial giants, influencing everything from their surface activity to their interactions with the surrounding cosmos. Magnetic fields in massive stars are incredibly strong, often thousands of times more intense than the magnetic field of our Sun. These fields are generated by the churning motions of charged particles within the star's interior, creating a dynamic and ever-changing magnetic environment. One of the most dramatic effects of these fields is their ability to shape stellar winds. The intense magnetic forces can channel and accelerate the flow of charged particles streaming away from the star, sculpting these winds into intricate patterns and even launching them at incredible speeds across vast distances. But that's not all. Magnetic fields also give rise to spectacular stellar flares. These sudden bursts of energy occur when magnetic field lines become twisted and snap, releasing enormous amounts of radiation and charged particles into space. These flares can be so powerful that they outshine the star itself for brief moments, creating dazzling displays that astronomers can observe from light years away. Beyond their influence on stellar winds and flares, magnetic fields also play a key role in shaping the overall structure of massive stars. They can affect the star's rotation, slowing it down over time as magnetic forces interact with the star's outer layers. This interaction can also lead to the formation of starspots, regions on the star's surface where the magnetic field is particularly strong, causing localized cooling and darkening. Interestingly, the presence of strong magnetic fields can even influence how massive stars end their lives. As these stars approach the end of their lifespans, their magnetic fields can impact the dynamics of their core collapse, potentially altering the nature of the resulting supernova explosion or the formation of a neutron star or black hole. As we continue to explore the mysteries of massive stars, it's clear that magnetic fields are not just a side note. They are a fundamental force that shapes the behavior, evolution, and ultimate fate of these cosmic giants. Next, we'll dive into how massive stars in other galaxies are helping us piece together the story of the early universe. Now, let's journey beyond our own galaxy and explore how massive stars have been discovered in the far reaches of the universe. These distant giants are not just fascinating in their own right, they also serve as cosmic time capsules, offering us a glimpse into the early universe and the conditions that shaped star formation billions of years ago. Massive stars have been observed in galaxies millions and even billions of light years away. These observations are made possible by powerful telescopes that can peer deep into space, capturing the light emitted by these stars long before our solar system even existed. What makes these discoveries so remarkable is that they allow astronomers to study how massive stars formed and evolved in environments vastly different from our own Milky Way. For example, in some distant galaxies, massive stars are found in regions with much higher densities of gas and dust compared to what we see in our local universe. These extreme conditions can lead to the formation of stars that are even more massive than those we observe closer to home. By studying these stars, scientists can piece together how the early universe's unique environment influenced the birth and growth of these celestial giants. One of the most exciting aspects of discovering massive stars in other galaxies is the insight they provide into the universe's history. Because light takes time to travel across vast distances, observing these stars is like looking back in time. The light we see from a massive star in a distant galaxy might have begun its journey when the universe was just a fraction of its current age. This allows astronomers to study how star formation has changed over billions of years, shedding light on the processes that shape the cosmos as we know it today. Moreover, these observations help us understand the role massive stars played in the early universe. Their intense radiation and powerful stellar winds likely influenced the formation of galaxies, triggering the birth of new stars and enriching their surroundings with heavy elements. By studying massive stars in other galaxies, we can better understand how these processes unfolded on a cosmic scale, shaping the universe into what it is today. As we continue to explore the universe, the discovery of massive stars in distant galaxies reminds us of the incredible diversity and complexity of the cosmos. These stars are not just distant points of light, they are key pieces of the puzzle that help us understand the story of the universe itself. Next, we'll look ahead to the future of massive star research and the groundbreaking discoveries that await us. As we look to the horizon of cosmic discovery, the future of massive star research shines brighter than ever. Cutting-edge missions and advanced technologies are set to transform our understanding of these celestial giants, unveiling secrets that have remained hidden for billions of years. One of the most exciting tools in this quest is the James Webb Space Telescope, a marvel of modern astronomy that promises to revolutionize how we study massive stars. The James Webb Space Telescope, with its unprecedented sensitivity and ability to observe in infrared light, is uniquely equipped to peer through the dust and gas that often obscure massive stars. This allows scientists to study these stars in incredible detail, even in distant galaxies. By capturing the faintest traces of light from the early universe, the telescope will help us understand how massive stars formed and evolved in environments vastly different from our own. But the James Webb Space Telescope is just the beginning. Future missions such as the Nancy Grace Roman Space Telescope and ground-based observatories like the Extremely Large Telescope will further expand our capabilities. These instruments will not only provide sharper images of massive stars, but also allow astronomers to analyze their chemical compositions, magnetic fields, and interactions with their surroundings in ways never before possible. One of the most exciting possibilities is the ability to observe massive stars in the earliest stages of their formation. By studying these young stars, scientists hope to uncover the processes that lead to their incredible size and luminosity. This could shed light on why some stars grow to be so massive while others remain relatively small, offering clues about the fundamental laws that govern star formation. Additionally, these missions will help us explore the role of massive stars in shaping the universe. By observing how their intense radiation and stellar winds influence nearby gas clouds, we can better understand how they trigger the birth of new stars and enrich their galaxies with heavy elements. This knowledge could provide a deeper understanding of how galaxies evolve over time, from their earliest beginnings to the present day. The future of massive star research is not just about answering existing questions, it's about uncovering new mysteries. As we push the boundaries of our technology and knowledge, we may discover phenomena we can't yet imagine. Each new observation brings us closer to understanding the life cycles of these cosmic giants and their profound impact on the universe. With every mission and every discovery, we are rewriting the story of the cosmos. The James Webb Space Telescope and its successors are not just tools for exploration. They are gateways to a deeper understanding of the universe's most massive stars and the role they play in the grand tapestry of space and time. Next, we'll explore how these stars might even hold clues to one of the universe's greatest mysteries, dark matter. Now, let's turn our attention to one of the most intriguing mysteries of the cosmos, the connection between massive stars and dark matter. While dark matter remains invisible and elusive, scientists have proposed fascinating theories about how these colossal stars might play a role in its existence and distribution. One compelling idea is that the explosive deaths of massive stars, supernova, could be linked to the creation of dark matter particles. When a massive star collapses and explodes, it releases an enormous amount of energy and matter into space. Some researchers suggest that this process might also produce hypothetical particles, such as weakly interacting massive particles, or WIMP, which are prime candidates for dark matter. These particles, if they exist, could help explain why dark matter makes up such a significant portion of the universe's mass. Another theory explores how massive stars might influence the distribution of dark matter. The intense gravitational fields of these stars, combined with the shock waves from their supernova, could potentially alter the way dark matter clumps together in galaxies. This interaction might help explain why dark matter forms the invisible scaffolding that holds galaxies together, shaping their structure and evolution over billions of years. While these theories are still in the realm of speculation, they highlight the profound connections between the visible and invisible aspects of the universe. Massive stars, with their immense energy and dramatic life cycles, might hold clues to understanding dark matter, a substance that, despite being invisible, plays a crucial role in the cosmos. As we continue to study these celestial giants, we may uncover new insights into how they interact with the mysterious fabric of dark matter. Each discovery brings us closer to solving one of the universe's greatest puzzles, revealing the intricate ways in which massive stars shape not just the visible universe, but the hidden one as well. Next, we'll dive into how massive stars have inspired myths, legends, and cultural stories throughout human history, showing how their brilliance has captivated our imaginations for centuries. Now, let's explore how the brilliance of massive stars has not only shaped the cosmos, but also ignited the human imagination across cultures and centuries. These celestial giants, with their awe-inspiring luminosity and dramatic life cycles, have long been a source of wonder, inspiring myths, legends, and stories that reflect our deepest hopes, fears, and curiosities. In ancient Greek mythology, the constellation Orion, often associated with a massive star, was believed to be a mighty hunter placed among the stars by the gods. The bright star Betelgeuse, one of Orion's shoulders, was seen as a symbol of strength and power. Similarly, the Pleiades star cluster, home to several massive stars, was revered by many cultures, from the Greeks to the indigenous peoples of the Americas, often symbolizing unity, guidance, or even the spirits of ancestors. Moving to the east, Chinese astronomy tells of the star Canopus, one of the brightest in the night sky, which was associated with longevity and wisdom. In Hindu mythology, the star Sirius, known as the dog star, was linked to the god Rudra, a deity of storms and healing. These stories reveal how massive stars were woven into the cultural fabric of societies, serving as celestial markers of time, navigation, and spiritual significance. Even in more recent history, massive stars have continued to captivate us. The supernova of 1572, observed by the Danish astronomer Tycho Brahe, was interpreted by some as a divine omen, sparking debates about the nature of the heavens. Similarly, the star Eta Carinæ, with its dramatic outbursts in the 19th century, has been a subject of fascination, inspiring both scientific inquiry and artistic expression. These examples show how massive stars have transcended their physical existence to become symbols of human creativity and curiosity. They remind us that the night sky is not just a scientific frontier, but also a canvas for storytelling, where the light of these stars continues to illuminate our shared cultural heritage. As we reflect on the role of massive stars in mythology and culture, we're reminded of their enduring power to inspire. Next, we'll turn our gaze to the ongoing search for even more massive stars as astronomers push the boundaries of what we know about these cosmic giants. As we marvel at the colossal scale of stars like R136A1, it's worth asking, could there be even more massive stars waiting to be discovered? The search for these cosmic giants is far from over, as astronomers continue to push the boundaries of what we know about the universe's most massive stars. One of the biggest challenges in this search is the sheer rarity of such stars. Stars exceeding 250 times the mass of our Sun are incredibly uncommon, and their short lifespans make them even harder to spot. By the time we detect their light, many of these stars may have already lived out their explosive lives. Another hurdle is the distance and obscurity of these stars. Massive stars often form in dense, dusty regions of space where their light can be blocked or distorted by interstellar material. This makes it difficult for telescopes to capture clear images or gather accurate data about their size and mass. Despite these challenges, advancements in technology are opening new doors for discovery. Space telescopes like the James Webb Space Telescope, with its ability to peer through cosmic dust, are giving astronomers unprecedented views of star-forming regions. Ground-based observatories equipped with adaptive optics are also helping to sharpen our view of distant stars, revealing details that were once hidden. One promising area of research is the study of star clusters in distant galaxies. These clusters, often teeming with young, massive stars, could hold clues to the existence of even larger stars. By analyzing the light and spectra of these clusters, astronomers hope to identify stars that push the limits of what we thought was possible. The search for more massive stars isn't just about breaking records, it's about understanding the extremes of stellar physics. Discovering a star more massive than R136, A1 could shed light on how these giants form, evolve, and ultimately shape the universe around them. As we continue to explore the cosmos, the possibility of finding an even more massive star reminds us that the universe is full of surprises. Next, we'll delve into how the intense radiation and stellar winds from these stars impact nearby exoplanets, shaping the potential for life in their vicinity. Now, let's turn our attention to the cosmic neighborhoods where these massive stars reside and the profound influence they have on their surroundings. The intense radiation and stellar winds from massive stars don't just shape their immediate environment. They can also dramatically impact nearby exoplanets, potentially making them uninhabitable. Massive stars emit an extraordinary amount of ultraviolet radiation, far more than smaller stars like our Sun. This radiation can strip away the atmospheres of planets orbiting too close, leaving them barren and lifeless. Imagine a planet bathed in constant, searing UV light, its surface scorched and its atmosphere blown away like dust in a cosmic wind. But it's not just radiation that poses a threat. The powerful stellar winds from massive stars, which can travel at speeds of millions of miles per hour, can erode planetary atmospheres over time. These winds carry charged particles that bombard nearby planets, stripping away molecules and creating hostile conditions. For any potential life on these exoplanets, the combination of intense radiation and relentless stellar winds creates a double-edged sword of destruction. Even planets that lie farther away aren't entirely safe. The sheer energy output of a massive star can heat a planet's surface to extreme temperatures, making it impossible for liquid water, and thus life as we know it, to exist. In some cases, the gravitational pull of a massive star can also destabilize the orbits of nearby planets, flinging them into chaotic paths or even ejecting them from their systems entirely. However, not all hope is lost for life in these extreme environments. Some exoplanets might find refuge in the protective shadow of a massive star's magnetic field or behind thick layers of atmospheric shielding. Others could develop unique adaptations to survive in such harsh conditions, though this remains purely speculative. The study of how massive stars affect exoplanets is still in its early stages, but it's a crucial piece of the puzzle in understanding the potential for life beyond our solar system. As we continue to discover new exoplanets, the role of massive stars in shaping their habitability will remain a key area of research. Next, we'll explore how the elements forged in the hearts of these massive stars are essential for life as we know it, connecting their explosive lives to the very building blocks of existence. Now, let's dive into the incredible connection between massive stars and the very ingredients that make life possible. The elements forged in the hearts of these colossal stars are not just remnants of their explosive lives. They are the building blocks of everything around us, including life itself. When massive stars reach the end of their lives and explode as supernova, they scatter their enriched material across the cosmos. This material includes essential elements like carbon, oxygen, nitrogen, and iron elements that are crucial for the formation of planets, oceans, and even the molecules that make up living organisms. Without these elements, the universe as we know it would be a barren, lifeless place. Consider this: the carbon in your DNA, the oxygen you breathe, and the iron in your blood were all created in the cores of massive stars. These stars act as cosmic forgers, transforming simple hydrogen and helium into the complex elements that form the foundation of life. It's a process that takes billions of years, but it's one that has shaped the universe into a place where life can thrive. The role of massive stars in the cosmic cycle of matter is nothing short of extraordinary. After a supernova explosion, the ejected material mixes with interstellar gas and dust, eventually forming new stars, planets, and even entire solar systems. This cycle of creation and destruction ensures that the elements necessary for life are continuously recycled and distributed throughout the galaxy. But the story doesn't end there. The heavy elements produced by massive stars also play a critical role in the formation of rocky planets like Earth. Without these elements, planets would lack the diversity of minerals and compounds needed to support complex ecosystems. In a way, massive stars are the ultimate cosmic architects, shaping the conditions for life to emerge and evolve. As we continue to search for life beyond our solar system, understanding the role of massive stars in creating and distributing these essential elements becomes even more important. By studying these stars, we gain insights into the conditions that make life possible and the likelihood of finding it elsewhere in the universe. Next, we'll reflect on the lasting legacy of massive stars and their profound impact on the cosmos, from shaping galaxies to creating the very building blocks of existence. As we bring our journey through the cosmos to a close, let's take a moment to reflect on the profound legacy of massive stars. These celestial giants are far more than just dazzling points of light in the night sky. They are the architects of the universe itself. From the moment they ignite in vast clouds of gas and dust to their explosive final acts as supernova, massive stars leave an indelible mark on the cosmos. Their influence begins with their immense gravity, which shapes the structure of galaxies, pulling stars and planets into intricate orbits. But their impact doesn't stop there. Through their lives and deaths, massive stars forge the elements that make up everything we see, touch, and are. The carbon in our cells, the oxygen in our air, and the iron in our blood all trace their origins back to the hearts of these stellar behemoths. Beyond their role in creating the building blocks of life, massive stars also act as cosmic recyclers. When they explode, they scatter their enriched material across the galaxy, seeding the birth of new stars, planets, and even entire solar systems. This cycle of creation and destruction ensures that the universe remains vibrant and ever-evolving, a testament to the enduring power of these stars. But perhaps the most awe-inspiring aspect of massive stars is their sheer beauty. From their brilliant blue-white light to the stunning nebulae they create, these stars are a constant reminder of the universe's capacity for wonder. They challenge us to look beyond our own world and imagine the vast possibilities that lie among the stars. As we gaze up at the night sky, let's remember that every star we see is part of a grand cosmic story, one that began billions of years ago and continues to unfold. Massive stars are not just distant objects, they are the threads that weave the fabric of the universe, connecting us to the past, present, and future of all that exists. Thank you for joining us on this journey through the universe's most massive stars. If you enjoyed this exploration, don't forget to like, subscribe, and hit the notification bell to stay updated on our cosmic adventures. Until next time, keep looking up. The stars have so much more to reveal. As we wrap up our exploration of the universe's most massive stars, let's take a moment to revisit the incredible journey we've taken together. From understanding what makes a star truly massive to witnessing the awe-inspiring power of supernova, we've uncovered 30 fascinating facts that highlight the profound role these celestial giants play in shaping the cosmos. Massive stars are not just distant wonders, they are the engines of creation, forging the elements that make up everything around us, from the air we breathe to the very fabric of our bodies. Their explosive deaths scatter these elements across the galaxy, seeding new stars, planets, and even the potential for life itself. Through their immense gravity, intense radiation, and dramatic lifespans, they influence the evolution of galaxies and the structure of the universe on a grand scale. But beyond their scientific significance, massive stars remind us of the beauty and mystery of the cosmos. Their brilliant light and the stunning nebulae they create inspire us to look up and wonder about the vastness of space. They challenge us to think beyond our own world and imagine the infinite possibilities that lie among the stars. As we conclude, let's carry this sense of wonder with us. The next time you gaze at the night sky, remember that every star you see is part of a story billions of years in the making. A story that continues to unfold with each passing moment. If you've enjoyed this journey through the universe's most massive stars, don't forget to like, subscribe, and hit the notification bell to stay updated on our cosmic adventures. And if you're curious to learn more, grab a telescope, explore the night sky, and let the stars guide your imagination. Until next time, keep looking up. The universe has so much more to